So M-polyfolds for real this time. And I am going to be a little bit lazy, and I've just clipped a couple of the definitions from this survey that I co-authored. Because these are not the official, printed definition by Hofer, Wysotsky, Zehnder, but they're, I think, just as rigorous and maybe a little shorter. I'm also, for now, going to completely push under the rug any kind of boundaries and corners. So we'll kind of just generalize Banach manifolds without boundaries. So, good old story. Well, what is a Banach manifold? It's a second countable Hausdorff space with charts and transition maps. Turns out that once you have the transition maps, the Hausdorffness actually becomes metrizability. So we might as well write that down from the beginning. It's not an extra condition. Right, and well, you need charts. So we need to say what the charts are. And you also need, you need the transition maps to be smooth in some sense, and that notion will be some kind of scale smoothness. So, charts. So let's see. We want open sets in our polyfold, M-polyfold. I might forget the M, right? So today, every time I say polyfold, there should be an M before, because we're not doing groupoids. So I want open subset covered by some local models. For a Banach manifold, the local models would be open subsets of a Banach space. For a scale Banach manifold, they would be open subsets of a scale Banach space. And ours are going to be scale retracts, whatever that is. That local model wants to be homeomorphic to the open subset in X. So let me start to write this down. So we want X covered with some index set by these open sets UI, which I would like to be homeomorphic via some continuous maps with continuous inverses to some local models. Oops. Right. So, what are these local models? So that's when it starts to become a little bit more funky. So, what is this scale retract? That's somehow here, and it comes from a scale smooth retraction. Now, you should not think of this in terms of any kind of topological retraction. A retraction is simply a self-map on some open subset of my scale Banach space that squares to itself. So projections are a good example. Or a retraction that keeps the one ball fixed and retracts everything else into the one ball. And then we simply call its image the retract, right? So I'm going to have a whole bunch of retracts. So there's a curly UI here, and that is the image now of some open subset UI in some scale Banach space. So I've made sure that I call things U if they are open, and this O thing here is not open, right? Well, it's equal to this image here, but we'll see examples where that image of the retract is not open. This set here is open, and these this is an open cover. So, well, that's going to formalize the idea of somehow quotienting by ambiguities of the pregluing we had last time. And we're going to hopefully actually get to that. Right, and now obviously we need to ask ourselves what's happening with the transition maps. And so that's a little bit more funky now. So when I now have two different of these charts, I can intersect them in X. Oh, it's a different X, it's the same X. So UI intersect UJ. On the one hand, is mapped to by phi I from, well, the pre-image of UJ. So that's some open subset of OI. And now I don't have enough space, as usual here. So this sits in OI open. And it also comes via phi j from some open subset of OJ. Right. However, these sets are pretty weird, so there's no good way of saying there's any kind of smooth structure that gets preserved by the transition map. And so we're going to avail ourselves of the bigger ambient space. So this OI here is the image of the open set QI in E. And, well, the preimage of this under Ri should also be open because Ri is scale smooth, in particular continuous. So there's an Ri here. So this is now also open, and here in particular that means that it is an open subset of my scale Banach space. And what else? Well, this here is, Rj of Qj, and as such sits in my open, my not open, but is a subset of my Banach space Ej. And I might want to think of that as an inclusion map, actually. So now I can actually produce a transition map. Well, the transition map really is this thing here. But I'm going to extend it through Ri, as a map from this open set to that open set, which I am going to include into Ej. So that's a map from an open set of a scale Banach space I to a scale Banach space Ej, not necessarily an open set there, but I don't care. So I can ask this to be scale smooth in the sense we discussed. So what really happens here is, right, I'm not just looking at the transition map, I'm looking at the transition map with a sort of precomposition by kind of projection to this set on which the transition map is actually defined. So one would think that that's a property of somehow the maps together with these projection maps Ri.
Why then extend to EI?
why can I extend to EI? So let's see. Because, right, so OI is a subset of EI, and it is the image of RI.
But your R is from EI.
Oh, yeah, sorry, my R is, okay, yes, I should map from this open subset here. So that's, yeah, right, that's an open subset. And, yeah, so I'm not, I don't really even know of an example where you're not retracting from the entire Banach space. But this is the general definition here. Okay, so right. So here's that definition written out of what do we mean when I have this O map from O to R. That's now I should think of phi j inverse. No, phi j, right, inverse composed with phi I. There are two different retracts, and I'm calling that a SCK map, or in particular scale smooth map, if this composition here is smooth, right, where I pre-compose with the retract and I post-compose with this occlusion map. Oh, and that, interesting, typos, that should be that kind of F. Pretty obscure question.
Are the E's different, or are you just...
They can be completely different, yes. Oh, right, so I should give this a subscript also. Yeah. Right. We'll see, I mean, this, if we made an M-polyfold for Gromov-Whitman invariance, then sometimes the E will just be sections of the pullback bundle of one smooth curve, and near the broken curves they're going to be products of pullback sections over two curves. Different, however, is kind of relative. They're all going to be Hilbert spaces, and they're all going to be separable Hilbert spaces, so on some level they're all the same. But the transition maps certainly are not necessarily going to map to an open subset. So the differential of these transition maps are not going to be isomorphisms on the Hilbert spaces. So, yeah, we will see examples. I figured I change philosophy for once and start from formal definitions. So in terms of formal definitions, we start with this wonky idea of sort of taking a retract as local model, and then the first question is, well, can you even make sense of scale smooth transition maps? And the answer is yes, because you have this ambient space. There's many more questions of how does this actually make sense as a local model for any kind of suitable, generalization of a Banach manifold. And one obvious question is, what about tangent spaces? And so there's a nice observations here that tangent spaces totally make sense. So here's first just a definition of what is the. So right, what I didn't quite point out so much is the retraction somehow wasn't really part of my data in the polyfold chart. Right, so my M-polyfold chart just consists of a scale retract O. I'm not fixing the retraction that maps to it. And so then when you're saying scale smoothness, you're actually allowed to choose a retract. So obviously we're going to need to worry about independence of definitions from the choice of retract.
How does the O look like usually?
How does the O look like in?
In U or in E?
Well, so one example that we're going to see very soon is, this is a finite dimensional example. So one example is half space with a line attached. But this would lie in, this is going to lie in R times L2 functions. So this is E, and this is O. So yes, maybe that's actually a good picture to have right here. So obviously, there is this nice ambient space. You have, as a vector space here, you have an idea of what the tangent space should be. And now we would like to make sure that, at every point here, what should the tangent space be? Well, here this looks terribly smooth. Here, you'd think you should find a two-dimensional tangent space. Interesting question is what happens at this point, where that line is not part of the. There's a fiber over one point here in R that is still 0 at that point. So, well, we want linear subspaces of this space here. And the linear subspace that you take is, well, you choose a retraction, and then you essentially just take the image of the linearized retraction. Which, in this case, well, restricted to the image of the linearized retraction, that is the identity. So makes it sort of believable that you get the right spaces here. Except, the problem is that these lines here are not, they don't lie in the plane, they lie in L2 of R. So what's nice about this? So one thing is that this comes with a splitting. That's maybe not so obviously relevant right now, but it's going to be very important for Fredholm theory. So the linearized retraction is now a linear map, and because R squared was R, its square is itself, so that is a projection. And it has a complementary projection, which is simply the identity minus dr. So these are complementary projections. And that means you get a nice splitting of your Banach space, in this case, as the image of dr at every point, and the image of the identity minus dr. So that's a direct sum, simply because the projection maps are continuous. And that's also, this here is also known as the kernel of dr. And somehow, when we then have operators that are really only defined on this stuff, they're really only going to be defined on this image, which makes sense to call the tangent space. but we will always have this canonical choice of complement. At least once we've chosen a retraction R, we're going to get these canonical choices of complements, and we can, do extra stuff to somehow fill up the operator on there. It's going to be the philosophy at some point. So, right. Obvious questions is what happens when I now change the retraction? Right, so if I have two scale smooth maps that square to themselves, and they have the same image, oops, that looks too much like an O prime here. Let's call that a U prime. I would like to say that the definition of this tangent space is the same, and indeed the claim is that the images of the differentials are in fact simply the same for any point in the retract. And so that means I can actually define the tangent space as this. So choice of retract might not be that important. And finally, there's one more little somehow thing that, well, there's a lot more things that you would like tangent bundles to do. But when you first saw the definition of a tangent bundle for a manifold, you probably saw it as kind of equivalence classes of paths or derivatives of paths. And that's really what it should be. So, really I should see all the vectors in this tangent space by little paths going through there. And that makes it a little fascinating to ask yourself, well, if you come in here, can't you turn maybe so fast that you're going to, well, are you going to see one or two dimensions here? So that, well, it's one question we can ask ourselves once I've actually defined the retract for this. But the lemma tells me that the path definition in the retract setting is actually the same one as this tangent space. So yet an alternative definition of this retract of the tangent space to the retract is something that actually does not depend on the choice of the retraction pretty explicitly, because I'm just going to take derivatives at zero of paths into my retract, well, which R in particular maps into my scale Banach space. I'm just going to ask them to be SC1 for now here, and go through P. So there's actually homework, figure out whether this should be SC1 or SC infinity. Somehow there's at least one typo in my paper right now. And I need to figure out whether that should be SC infinity or SC1. I'm actually going to guess SC1 because you're kind of wanting to get all directions and not just sort of the smooth directions inside of E. Right, and there's no R in this definition, so that also shows us that really tangent spaces make sense without having to choose the retraction. All right. So, right. Obviously, this is something I would call a finite dimensional polyfold, because it looks finite dimensional, and also most pieces have charts in finite dimensional manifolds. except this one point here, only has a neighborhood that looks like that stuff, and the only reasonable M-polyfold chart that this little neighborhood has actually is in infinite dimensions. So, that sort of ties in nicely with the complaints I had about Kuronishi structures, where we had to sort of stick lower dimensional pieces into higher dimensional pieces, and it was really unclear what the topology should be near that, attaching point. There was no first countability of the obvious quotient topology when you just stuck a lower dimensional piece into a higher dimensional piece, and the answer here is that these are not actually fixed dimensional pieces that get stuck into each other. That it's just one subset of a large space that's, has a perfectly nice topology. So, but we want to see how that guy comes about, and so we should reproduce this guy, and I'm going to do that by retreating from retracts to splicings, which is also, if you read through HWZ literature, you'll see that the first polyfold papers actually are completely in terms of splicings. At some points they generalize that to retracts. So most generally, so the retracts I have in mind here will be retracts where I have kind of finitely many dimensions split off. In my scale Banach space, and what my map is, for some reason, points in E prime are called F here, is simply a family of projections, so linear projections, on E prime. So there's your family pi v, well, which in general could be parameterized just by some open subset, but right, so we want them to be projections. No, right, they're linear projections, and the key is, right, I asked this map to be scale smooth, which means I'm asking this projection to sort of be pointwise scale smooth. What I'm not asking is somehow v mapping to pi v to even be continuous as a map from U to somehow linear operators on E prime. And right, clearly, so, well, lemma, if this family of projections was continuous as a map to bounded linear operators, then this could not be the picture of the image of it, because the dimension of the images stays constant. So that means we should find some discontinuity of operators in the following example that's going to create this. So R times L2 functions on the real line, two L2 functions on the real line. The nice thing is, well, R is a finite dimensional set, and so it itself is its scale structure, so I'm allowed to write the double line on it. I should also write the double line on L2 functions, thinking, right, I'm going to make it a scale space by this filtration of weighted Sobolev spaces. I'm not going to deal with that today. So I'm going to do something completely brutal. I will project onto a one-dimensional line generated by some vector beta sub v, as long as v is bigger than 0, and when v is 0, or less than 0. I'm just going to project to 0, where my beta of v is. So I'm going to start off with a little bump function. For that to be a projection, I would like beta in the L2 norm to be 1. And then beta sub v is simply going to be the bump function shifted out to be centered at 1 over v. That does not converge as a function in L2, right? Because its norm is 1, and in the limit, well, you know, it's everywhere 0 pointwise, but yeah, its energy went off to infinity. However, it does converge weakly in L2 to 0. Because I'm supposed to test it against any other L2 function, and you know that L2 function has finite mass. So if I go further and further out with my little bump, I'm just going to see less and less of that mass. And so that weak convergence here means exactly that I have this pointwise, well, continuity and in fact scale smoothness. I'm not going to have any continuity as a boundary. As an operator.
So the LE prime, so the bounded linear operator on E prime
Yeah.
doesn't have a scale balance.
Ooh boy, you can probably give it a scale structure.
But it's not like functorial, like harm from that product to E prime is harm.
No. I mean the topology is completely different. I mean, you could even just instead of E prime just take the Banach space that's E0 here. So that would just be when I take linear operators on L2 by themselves. So what I want to say here is that, you know, this map from R times L2 to L2, this will be continuous and in fact scale smooth. As a map to bounded linear operators on L2, it is not continuous. Because it's, you know, you're projecting to something of norm 1, you know, but v bigger than 0, and then you're projecting to 0. So, dirty tricks, right? So let's see how that plays out here. Right, so my, well, image is now pretty trivially read off, right? Image is the real line times generated by this vector, or 0. Right, so what I didn't say, right, so once you have a splicing, that's like your retract, right? So splicing is this family. Pi v makes this retract by fiber-wise projection. And then the splicing core simply is the retract which you get, right, from the pairs of points that are in the image. So I like to think of it as this sort of vibration of, you know, the images of my family of projections. And so that's what I'm depicting here. Right, this whole thing sits over R, and sort of this really another direction, which is L2 functions on R. And as I go, you know, if I look at a sequence of points VI that goes to 0 from the right, then each of these fibers here, you know, they look like a trivial vibration, but really, you know, they are lines generated by different vectors. So it's really a family of lines that turns, you know, pretty fast and faster as you get to 0. It sort of swoops out. Actually, in fact, I think the entire space. Oh, I mean, no, you're not. You're not quite. It swoops out an infinite dimensional subspace of L2 functions. But it weakly converges to 0. So in some sense, sort of this subspace here weakly converges to fiber 0. That's now this fiber here over 0. And then beyond that, your fiber simply is 0. That's the V less than or equal to 0. So that's really what you should think when you see this picture. It's like not sort of a nice flat half plane. It's a half plane that somehow turns. And sort of in some sense, there's a lot of curvature as you go into that point. So
why
yeah.
is this smooth, the pi? Is it like when you go to 0 and suddenly beta B disappears?
Right, so let's see. I only have to ask about smoothness in V, right? Because in E, it's simply...
so beta V also has values, and it's also like has maximum goes to 0.
No.
Or beta V is just shift of, it's like shift.
So, hold on. You might not know the difference between. So the key here is this is not converging to 0. What is converging to 0 is the L2 inner product of beta V with any F. And so for all F in L2. And that's simply because, so you could check this for a dense subspace, namely the one of F with compact support. Right? And so if F has compact support, then, once you've shifted far enough out, this is simply going to be 0.
So then why the critical locus is 0? Why 0?
At 0?
Yeah. Why 0?
I simply defined it that way, right? So I defined the projection to be 0 at 0.
So then why is it continuous?
Well, that's right. So I need to check that this map here is continuous, right? V comma F going to this. Right?
Yeah.
And what I just checked is as V goes, if I fix F and I let V go to 0, then this goes to 0 as V goes to 0.
So what if beta V when V is close to 0?
It's when V is close to 0, it's a bump function that sits very far out here. Oh, sorry, yes.
Oh, I see.
Yes, this is V inverse, right?
Okay.
So I'm running
I see.
far out, and as V goes to 0, that bump function just goes off on a tangent. Good. Right? That's the beauty of infinite dimensional spaces. You can actually send things to infinity, and they sort of weakly converge to 0. Right. Homework, figure out what actually is the tangent space here at the point 0, 0 to my splicing. In particular, is it 1 or 2-dimensional? Okay, so that is a nice example. It's good to have. These are not polyfolds we will ever deal with. Right? So one common misconception is that we're going to give our moduli spaces, our Gromov compact moduli spaces, this local structure like this. No, that is not the case. Our perturbed moduli spaces are going to be smooth manifolds in the old sense. Really, we're only going to be interested in, very infinite dimensional versions of this. And in fact, we're only really interested in one splicing, namely the one that we get from pregluing. So, that was kind of my functional definition of M-polyfolds. M-polyfolds are whatever gadget you get when you declare the pregluing map as a chart map. Right. So now I'd better explain to you how the pregluing map actually is, gives you a splicing. And I'm going to simplify life by thinking about not an ambient space for Gromov-Witten invariance, but one for the compactified Morse space of finite length trajectories. When I take a Morse function on Rn that only has one critical point, namely at 0. So then the points in my moduli space, or the points in my fattened up moduli space, should be, on the one hand, finite length paths. And I chose H1 because, that makes them at least C0 here, of any length. And then one thing can happen, it can break at 0. And so I should somehow allow myself a half-infinite path converging to 0 and another half-infinite path. And those again here, I can make a connected topological space by pregluing. And now I'd like to not just topologically define the neighborhood of a broken curve here, but I would actually like to give it the smooth structure. So claim is that this here is an M-polyfold, and I ought to give it an M-polyfold chart near a broken curve. So I need to start with an open set, right? So the open set is something that I get from pregluing, right? So this is my open set here in X. That's open by definition of the topology via, right. And pregluing now has become this little plus sign, but it's the same formula. So, right, so near a broken curve, gamma 0 minus gamma 0 plus, I ought to take two curves that are very close to that and some gluing parameter. If it's infinity, I don't glue them. If it's a finite gluing parameter, I shift them relative to each other a little bit, actually a lot, because, let's see, right, gamma minus is defined from 0 to infinity, and I need to start defining things at minus L. So I'm going to declare L as R, right, and then this starts at minus R. And so I shift gamma minus sort of to the left in the domain, I shift gamma plus to the right in the domain, and I interpolate between, say, minus 1 and 1, just cut off and turn the other one on. Totally brutal construction, but well, it kind of looks scale smooth, right? Because we have we multiply, we add, and we shift. So in this gluing parameter, we're probably just only going to have scale smoothness. So now I ought to see the M-polyfold chart here in this picture. So the thing that's surjective, is going to be a little bold and declare this as an interval here. And I need a scale Banach space. I'm just going to take these with my favorite scale structure. And well, previously I wrote somehow pregluing is a map from here to my open subset, but that was not part really of the structure of an M-polyfold chart. Right? What is part of that structure is some kind of retraction. Oops. I like to call them rho, but somehow Hofer calls them R. To some decent enough space, right? So that should be my retract now, O. Right. And O will be, right, my retraction actually is going to be sort of coming from a family of projections. Right, so with that, my retract is going to be the union. And now I'm going to need to be a little bit careful here. So the union times some image of the pi r. I want to write r here, but that interval here is not an interval sort of in Rn, right? So I'm going to need to identify this with a small interval in R. And now we're in a situation where this is also not an open subset of R, but it's one with boundary. But that's okay because we actually expect that to be boundary. I just haven't defined polyfolds with boundary. But, well, they have boundary if, this parameter is allowed to have boundary. This choice here actually ends up being pretty subtle. That's why it has a name. So the choice of this homeomorphism is called gluing profile. And I'm going to call it V, right? V of R. So with that, really, I ought to take V of R here. So which sits inside the scale Banach space, well, in the scale Banach space with boundary 0 infinity times E, where E is this gadget now. Okay, and now I'd like to have a homeo phi. Right, that would be part of my M-polyfold chart. And how do I do this? Well, so phi obviously off a point here should be the pregluing. But I'd like this to be injective, so I need my projections to get me to a complement of the kernel. And the nice thing now is I have cheated myself into a situation where this pregluing map is actually linear. right? I mean, not in R, but in gamma minus and gamma plus, it's linear. I manage that by taking my ambient space as Rn. So in general, you're going to have to, like, you know, the linearity is going to happen on some pullback tangent bundles, and so you're going to have a whole lot of, you know, local charts and exponential maps in the picture. That's the reason why I wanted Morse functions on Rn. So wait, is that still? It's still working. Okay, so since it's linear, I can declare that I would like pi r to simply be the projection to a complement of the kernel of this linear map. As long as r is less than infinity, and, well, I haven't defined pregluing for r equal to infinity, so at r equal to infinity, I'd like the projection to simply be the identity. Of course, there's a lot of projections with the same image, so now the challenge now is to find a projection that will be scale smooth, you know, pointwise. So, but this is the implementation, you know, of pregluing as an M-polyfold chart map now. So we're gonna have to find this splicing, you know, which is a splicing, so we're gonna need to, you know, make this family of projections scale smooth, and then pregluing is, you know, gonna, well, I mean, it's continuous from here to there. I'm going to make it bijective by restricting to the right space. I then need to still wonder whether the inverse is continuous. It is going to be. So, and the key to making pregluing into a nice, to making this projection here. So this needs to be a very special one. And the key is something called anti-gluing or anti-pregluing. So the idea is, well, there's a linear algebra idea and a sort of just keeping track of data idea. So I'm going to define, not quite yet, but in a bit, a map that's sort of not pregluing but anti-pregluing. And the idea is that this should also be linear in gamma minus and gamma plus, and it should keep track of the data that the pregluing forgets. So if I manage to write down a decent enough linear map that does that, then for finite R, right, the product of these two maps from my scale Hilbert space to some other space is actually going to be an isomorphism. So the wonky thing is that, well, with R, the target here changes, right? So E is, you know, two half-infinite intervals, or functions on two half-infinite intervals, and I'm mapping two, well, functions on the finite interval. And you can imagine, so that means you're losing an infinite tail of both gamma minus and gamma plus, and so you're just going to put those tails together the other way around, and we're going to do that pictorially. You're going to see functions on the real line. and they're going to satisfy something extra. I'm going to go to 0 at plus minus infinity. And I think that's all. Right? But again, this is, well, it's a Hilbert space. So this is an isomorphism of Hilbert spaces. And then linear algebra tells me that I get a splitting, even just on the level of Hilbert spaces, into the direct sum of the two kernels. And now I can, use that splitting to project onto. Now I'm going to use this as complement. This is my chosen complement. And I can now more rigorously define pi r as the projection along the kernel of the plus gluing, because I don't want to actually change the value of the plus gluing as I project onto the kernel of the mass gluing. So, in a little bit more formulas, what I'm doing is I'm mapping gamma minus gamma plus to two possibly different vectors, both half infinite. I'd like them to have the same pregluing still. But I'd like them to have anti-pregluing 0. And because that's an isomorphism, this is going to have a unique solution.
To turn a modular space into a M-polyfold, you always have canonical retraction. The choice of
The retraction? No, that's really, so what's going on here, right? So we start with a Morse moduli space here, right? I chose a big ambient space. I topologized that big ambient space, right? So that's already a fantastic choice there, right? Your moduli space itself doesn't necessarily know about that. And the topologizing here, it's sort of guided by the topology that I know works there, but there's different pregluing maps that I could write down now, right? That sort of give me that topology. And there are actually pregluing maps that you can write down that will not work. That don't give you charts.
So there's essentially one way of producing M-polyfold.
No. You could probably come up with different ways that are not necessarily equivalent. So somehow the specific choice of pregluing is going to be part of the structure somewhat. So in particular, so if you did, I don't know whether I mumbled about this, just to sort of do gluing for Morse spaces and somehow do classical gluing analysis there. I don't necessarily need to do this. I could instead do the pregluing where I run around along this path and then I accelerate and get myself in finite time to the critical point, stay there for a while, and then sort of accelerate out of here and run through gamma plus a little. That's still going to be close to there. I made a small error. I could run my implicit function theorem. I'm going to find an actual Morse trajectory nearby. The problem with that pregluing map is that it's not onto what I would like to be a neighborhood here, because they're all paths that stay at 0 for a while. There's nothing that sort of goes by nearby. So if I tried that map here, it would not map onto what I think is an open subset here. And so I wouldn't be able to get a nice retraction out of it. So, so I've made a specific choice here, right? I made the choice of shifting by a certain amount, and I made a choice of this cutoff function. And I'm making this choice of this gluing profile. And I believe the choice of cutoff function isn't relevant, but the gluing profile really gives you not compatible polyfold charts. But we're going to see a specific preferable gluing profile. That's the point. Right, so I chose this formula here, and I'm also going to make a choice for this formula of the anti-pregluing. But it's going to be a very specific, explicit choice, and then I'm going to run this linear algebra to get the splicing. So let's actually do that. So here's my splicing. So that's my scale Hilbert space. Right? Here I have an isomorphism between these Hilbert spaces, and the way I'm sort of being very unimaginative, right? There's sort of beta and 1 minus beta, so I'm just going to somehow switch the two, right? I should, here, cut off gamma minus somehow for very positive values, and I should do the opposite with it, and keep track of the very positive values of gamma minus, and the same thing with gamma plus, and I should keep track of the very negative values of gamma plus, and really there's a beta minus 1 instead of a 1 minus beta there, just because I want a matrix to be invertible at some point. So pictorially, right? So two paths, parameterized by two half-infinite intervals. You get the pregluing by shifting them a little, and just looking at the values up to a fixed number of gamma minus. Then you have this linear interpolation, and then you take the values of gamma plus from some interval out here. So, whoops. So let me try to keep track of the parts that I've actually have. Let's see. Right, so gamma minus, so this bit here, for the shifted one lives here, and for the non-shifted one lives there. The gamma plus is that part near the boundary of the interval. So, actually, up to minus 1, I really have that. So, that means I should have the remainder go someplace else. So in particular, this part here, up to infinity of gamma minus, which is out here, is going to go someplace. That's going to go here for the anti-gluing, and the part of gamma plus that's out here, right, that's this minus infinity end that's getting shifted out here. So that means that somehow this path parameterized by the full real line somehow starts and ends at 0, because that's where they converge to. And it gets interpolated at some place, so it's going to be continuous, and it's going to come back in with minus gamma minus, just because that's what I did with linear algebra. So I'm kind of splitting the information that I have from these two half-infinite paths into one finite path and a little loop from 0 to 0. So, and right, so on the pink intermediate part, I just linear algebra to see that I'm actually keeping track of all the data. So linear algebra, or in a moment explicit formulas. So that's a completely explicit formula. It really only depends on, again, my cutoff function, well, and the choice of the gluing profile that translates large numbers to small numbers. But this is all going to be here in terms of, well, let me keep this guy here for a moment. Capital R. So let's see. Right. I was going to rewrite this formula here in terms of matrices. So, right, my projection takes gamma minus gamma plus to eta minus eta plus. So I'm going to encode the plus gluing this thing here first as a matrix. Now I'm confused. Let's see. So the matrix is, well, shift in R direction on the first factor, shift in minus R direction on the second factor. So these are shifts. And then I ought to preglue. Oh, actually, right. So I'm going to preglue and anti-preglue at the same time, because why not? So the pregluing is going to come with weight beta and 1 minus beta. And well, so now I could do something in the second row, and it doesn't matter what I do, because in a moment I'm going to project it out to 0. So I'm going to forget that. So I'm going to multiply that with this matrix, so I can write down whatever I want to write down there, and it's nice to write down that anti-pregluing matrix. Because now this is this so this together actually is the, oh boy, isomorphism that I have here, right? So that's in matrix writing that isomorphism, and now I'm supposed to invert that right after I've projected down. But that matrix now has an inverse. So and the shift also has an inverse simply by shifting back. That's not a terribly bad formula, and it becomes a not so terribly bad formula when you write that out, but I wasn't going to do that in real time. So, oh boy. There. Right. So let's see. Right. So this projection here, right, for any R, right, is going to be linear in gamma minus and gamma plus. That's the good news. It seems to, the first factor wants to reproduce gamma minus because it multiplies with a cutoff function that's supported at very, very positive values. Let's see. This is, beta is 0 when this becomes bigger than 0. So as soon as you're right? No, beta is 1, right? As long as this is less or equal to 0. Right? So this is 1 up to about r. So we keep track of more and more of gamma minus as you let r go to infinity. And beta times 1 minus beta is always a function that's just supported on an interval of length 2, right? So, and that kills a little piece of gamma plus that's also shifted drastically. And you have a symmetric situation in the other component. So this looks terribly scale smooth. The only problem really is what happens when you, what happens when you go to r equal to infinity or v equal to 0. You know, that's a boundary, but really we would like our derivatives to make sense there, to converge. And it turns out that you need a pretty drastic gluing profile to get those derivatives to converge. So this is called the exponential gluing profile here. And this, you're free to make that choice. I wrote down a very explicit choice because I don't, in the end, want my Gromov-Witten invariance to depend on choices. However, I'm now going to need to worry, really, if somebody else defines Gromov-Witten invariance the pedestrian way, how that relates to this choice of gluing profile. And that is actually not somehow the geometrically natural gluing profile. That's one of the pains in the Gromov-Witten paper, where they use this gluing profile to make a new smooth structure on Deligne-Mumford space, which is not the complex smooth structure. So, challenge for the next generation is going to be to marry those two constructions, or understand why you really, can you push one or the other? How do we get somehow the canonical complex structure of Deligne-Mumford space sort of encoded in polyfold world? But for now, we're just really happy that we have some kind of smooth structure. So, upshot, in a big scheme of describing a moduli space as the zero set of a section, where are we? So, on object level, we had to cover our moduli space with Fredholm descriptions. We did that near smooth curves, and we then wanted to do that near nodal curves. And I decided let's do that just at the simplest nodal curve that I can think of. And now we can do that, right? So abstractly again, our setting, there should be some bundle over some base and some section, and the zero set should embed to an open subset. And we now have made that base space at least. Right? So, well, I didn't make it for spheres, I made it for paths. But let me just pretend I wrote down a good pregluing here, a good anti-pregluing. I did the same kind of linear algebra. So then my my local model here is going to be, in this case now, an open subset of a family of spaces that I get from gluing parameters A and images of the projections to somehow complements of the kernel of pregluing. And with that, my section, right, at points in here, right, will be taking, right, gluing parameter and curves that will be preglued to the d bar operator of the preglued thing, which means either d bar of both or d bar of the preglued one, depending on whether A is 0 or not. So what we did do is we gave this a smooth structure. Right? So this is now actually, well, it is an M-polyfold with one chart, because it is itself, the model for an M-polyfold. What we are going to need to do is we're going to need to ask ourselves about the bundle structure that there is, so that I can have these two different values in the fiber. And then we'd like this map here to be scale smooth in a, well, this is probably the sense of maps between polyfolds that we already had and Fredholm in some sense. And once we have that, we have, a local Fredholm description. Where, right, the last piece then, of course, is to say what this map is, right, but that then is simply the pregluing map. So this then goes to one or the other off. Well, to be totally anal, I should take the equivalence classes here. So that's exactly what we expect, and just to, oops. Okay, I'm not supposed to show you this. Right. There's a scale Banach space on which this whole thing would happen. And here's just, back to the preview from Monday. This is the same picture, hopefully you'll agree, as the one I had on Monday, where, pregluing just had a different sign, to my open subset of my moduli space. I wanted some projection to some subset on which that's a homeomorphism, and the rough idea was that I should do nothing with my projection at A equal to 0 and at A not equal to 0. I'm essentially going to see just the values away from the node. And that's really what this projection to the kernel of the anti-gluing does. Forgets the data there somehow in an organized fashion, in a smooth fashion, and so this is really that's what we did with this whole notion of retracts. I think this is really sort of the boldest idea in this whole theory, is to just say, let me take these weird subsets and let me just only remember the projection to them, or that there is a projection to them. And the deep mystery then is, why is there still some Fredholm theory? This is all a pretty fuzzy description here. It's a pretty weak notion of smooth structures and smooth maps. So the proof that needs to really happen is that there's a Fredholm theory for which an implicit function theorem holds. Which I'm going to try and show you the Fredholm theory, and hopefully it's going to look sufficiently convincing that you can believe that there is implicit function theorem. I'm going to state it. I'm not going to prove it. So that's where the papers of Hofer-Wysotsky are all available on the, in the abstract world. So that's checkable. So that will be the guiding question: is how in the world can we talk about Fredholm theory?